Okay, so let's talk about the analog to sorting, which is selection. Okay, and specifically selection in unsorted lists, because if we want to find if selection in a sorted list is very simple, and we'll discuss that in a second. So let's just talk. Let's just build off quicksort and remind ourselves that the problem with quicksort is that the pivot might not be the median. Okay, and in fact, the major problem with the quicksort is that the pivot might be the minimum or the max or something close to it. So let's think about this. So maybe the appropriate question to ask is, how long would it take us to find of a the median of a unsorted list? Okay, and so doing this, so one answer is simply to sort the list first, and then pick the middle element, right? So we discussed that actually in our in our reduction or recursion lecture, that we could reduce the problem of selection to the problem of sorting, right? We could first sort the array and then find the middle element. Okay, and then that works, but it seems like sorting should be a more difficult problem than selection, right? So is there a better way? Okay, so let's recall that the rank of an element is the rank of the element is simply the number which denotes that this element is the jth smallest element in A. Okay, so in rank 1 element would be the smallest element in the array. A rank 2 element would be the second smallest element in the array. A rank n element would be the largest element in the array. Okay, so the rank of the element is effectively its index when the array is sorted. Okay, so 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 the problem we have is that we want to find the rank n over 2 elements of the array. We have a unsorted array of n integers and a particular integer a, and we want to find the jth smallest element in A. Or in other words, something a little more concrete, if we want to find the median, j would be equal to n over 2. But it doesn't necessarily have to be the median. We're gonna leave this problem a little bit more broad than we need to, for the sake of the problems later on. But really, the selection problem itself is simply the problem of finding the jth smallest number in an array. Okay, so if j is the median, if j denotes the median, then j is equal to n over 2. If we want to find the minimum value, then j is equal to 1. If we want to find the maximum value, then j is equal to n. Okay. And let's just make this simplification. It doesn't really change anything, and we'll just say that the elements of A are distinct. Okay? Again, you don't have to make that distinction, but I don't want to get into the weeds and do a discussion of how to break ties and all of that. So let's just, for the moment, assume all the elements of A are distinct. Okay? So first algorithm we have to pick the jth smallest elements is simply to sort the elements in A and pick the jth element of the sorted list, right? And of course, this takes O of n log n. It takes O of n log n because, again, while we did say quicksort technically had a worst case runtime of O of n squared, I mean, we have merge sort, right? Merge sort pretty much always takes O of n log n, regardless of what you do. So this algorithm, sorting, then picking the jth element, we could safely say that it takes n log n time. Okay, so the question is, n log n time is pretty good, but is there O of n time algorithm? Is there an even better algorithm? Okay? And so, is there a better algorithm? So, it depends. Okay? What if we wanted to find the minimum value? Let's forget the median for a minute. Let's say we wanted to find the minimum value in an array. How long would that take? Well, I know that if we didn't care about sorting or selecting or whatever, finding the minimum value in an array just requires you to loop through the array once, right? You just say, okay, the current value, the first value I'm going to assume is a minimum for the time being. Then I'm going to keep going through the array until I find a value smaller. Once I find a value smaller, okay, this element is a minimum. Then I'll keep going until I find a value smaller. And once I reach the array, whatever recorded smallest value I found, that's the minimum. Okay? And how long does that take? It takes O of n time. And so, if J, if our rank is relatively small, or even relatively big, in fact, what can we do? Well, let's say J is 3, okay? We just keep a list of the 3 smallest values we've seen so far. And then at every element, we say, okay, is this element smaller than either the first value or the second value or the third value? No, no, yes. Then we remove whatever value, then we simply add the new smallest element to the group and remove the largest element in the group, exclude it. And then that would be our algorithm, right? So if J is very small, or J is very large, I should say. Well, if J is very small, and for maximum, we could pretty much do the same thing. Then we could get something along the lines of O of Jn algorithm, O of Jn time. Okay, O of Jn time. But that doesn't solve our central problem, which is that if we want to find a pivot that's more towards the center of the array, if our pivot is the median, if J is equal to n over 2, then this becomes O to the n over 2 times n, which is simply O of n squared, right? Which is terrible. Right? Again, this is a terrible, terrible way to find the median of an array because we have a faster algorithm here by sorting. Okay? So, what do we do in this case? Well, here's one option. We could go to the quicksort idea. Okay, we could go to the quicksort of the idea of finding a pivot and then breaking things on left and right to find the J smallest value. How? Well, let's say we find a pivot. Let's say we have an array. Okay, array in. Okay, and let's say we have some pivot xi. Okay, so xi gets put somewhere, let's say array sorted. Xi gets put somewhere in the divided array, right? In the partitioned array. And actually, that is a good word. We're going to do a parted. Okay? Xi, that pivot. So all the elements that were smaller than xi get put here. And all the elements that were larger than xi get put there. Okay? So we'll call these two subarrays A less and A more. So what's important here? If the size of A less, if this size is equal to J, then, or is equal to J minus 1, then it means xi is J. Then we just return the pivot. Return. Okay? But if A less is huge, if this side is larger than J, it means that the jth element has to be somewhere here. It means that the rank J element has to be somewhere there, which means that we recursively call QuickSelect on this to find the J smallest element. On the other hand, if A less is very small, right, is smaller than J, it means that the jth element has to be right here, somewhere here. Okay? In this case, we call QuickSelect to find the element that is rank K, which is J minus A less. Why is it this value? It's because the element that's ranked J, let's say the element that's ranked J is right here. That means that if we are getting rid of all these values here, if we recursively call QuickSelect on A more and get rid of these values, then this element is now rank J minus A less. No, A minus A less. Okay? So that's how the QuickSelect algorithm works. Exactly like Quicksort, right? The only cleverness is that we don't need to recursively sort both subarrays recursively called. Basically, in QuickSelect, the tree doesn't branch out. The tree only goes down one particular avenue. It goes to A more, QuickSelect A more, then QuickSelect A less, then QuickSelect A less, then QuickSelect A more. Okay? So, we don't need to do that. So, the partitioning step, as usual, takes O of n time to scan A. But there's a problem. How do we choose the pivot? How do we choose the pivot? Again, there's that problem where if we always choose the pivot to be the first element, there's a good chance, if we choose the pivot to be the first element, there's a good chance that the pivot, it could be, well, not a good chance, but there is a chance that the pivot could always be the smallest element of the array, as if A is sorted. So then, and we could be having J is equal to N. So this new algorithm could still end up taking O of n squared. That is not what we want. That's not what we want, right? The whole selection of the pivot thing is still a problem, right? If we were able to select a good pivot, if we were able to select a pivot that is K equal to N over 2, then we would have a QuickSelect algorithm that always partitions the array into halves, T of N over 2, plus O to the N, which here would be N plus N over 2 plus N over 4 plus N over 8, which is equal to 2N, O of N time. Okay? If we're able to choose a good pivot, then we could get something truly spectacular result. A linear time selection algorithm. But it's this damn pivot selection that's screwing us up. It's this damn pivot selection. If we're only limiting ourselves to choosing the first element of the array or choosing the middle element of the array always, there's always that chance that we choose poorly. Okay? So the question is, how do we choose well? Is there something we could do that doesn't require too much computation, but still allows us to choose a pivot that is good? And that's what we're going to talk about next.